We already know some special series. Those are the constant, geometric, and harmonic series. We also learned how to show if a series is convergent or divergent by using the definition, showing if the sequence of partial sums is divergent or convergent, or by using the divergence test to show if a series is divergent. In this lesson, we'll talk about another special type of series, which is what we call the p-series. Let p be a positive real number, so it cannot be negative, and p cannot also be 0. A p-series is a series of the form sum of 1 over n raised to p. If n is equal to 1, we have 1 over 1 raised to p, or that is just simply 1, plus 1 over 2 raised to p, plus 1 over 3 raised to p, and so on, as n goes to positive infinity. Now let's observe when is a p-series convergent or divergent. Note that if p is equal to 1, our p-series is just the sum of 1 over n, and that is the harmonic series, and we know that harmonic series is always divergent. Now for the case when p is not equal to 1, we can use the integral test. We did not talk about the integral test, so let's just skip this part and proceed to the conclusion of the test already. If you use this test, we have the p-series is convergent if p is greater than 1, and divergent if p is between 0 and 1. Let's try some examples. For our first example, let us determine if the series of 1 over square root of n is convergent or divergent. The given series is a p-series wherein the a sub n, that is 1 over square root of n, can be written as 1 over n raised to 1/2. So in this case, p is equal to 1/2, and 1/2 is less than 1. Thus, the series is divergent. What if we have this series 1 over n square root of n? You can write this as 1 over n raised to 3 over 2. Therefore, the given series is a p-series with p is equal to 3 over 2, and 3/2 is greater than 1. Therefore, this series is convergent. For our third example, let's have the series of n cubed plus 3 raised to n all over n cubed times 3 raised to n. This is definitely not a p-series, so let us transform first our a sub n and try to get a form of a series that we are familiar with. So in this case, we can separate our a sub n into a sum of n cubed all over the denominator plus 3 raised to n all over our denominator. For the first term, we can cancel n cubed, so we have 1 over 3 raised to n. And for the second term, we can cancel 3 raised to n, so we get 1 over n cubed. Now, the sum of 1 over 3 raised to n is a geometric series because you can write this as a r raised to n, where a is equal to 1 and r is equal to 1/3. And for a geometric series, if the absolute value of r is less than 1, then the series is convergent. Now for the second term, we have 1 over n cubed. The series of 1 over n cubed is a p-series wherein p is equal to 3 and that is greater than 1. And since p is greater than 1, this series is convergent. Both series are convergent, and by our theorem from the previous lesson, our given series is therefore convergent. For the second half of this lesson, let's learn another test to check if a series is convergent or divergent. Suppose our given series is a series of non-zero terms. That is, for every a sub n is not equal to 0. To use this test, we need to find the limit of the absolute value of a sub n plus 1 all over a sub n as n goes to positive infinity. If this limit is less than 1, then our series is convergent. But if this limit is greater than 1 or equal to infinity, then the series is divergent. Observe that we do not have the case wherein the limit is exactly equal to 1. If the limit is equal to 1, then this theorem, which is what we call, by the way, ratio test, is inconclusive. That is, we cannot use this theorem to conclude if a series is convergent or divergent. Now let's try to use this ratio test with some examples. First, let us determine if the series of -1 raised to n times 2 raised to n all over n factorial is convergent or divergent. So let us write a sub n to be equal to this. So always check if our a sub n's are non-zero before we use the ratio test. Well, in our denominator, -1 raised to n is never 0. That is either -1 or +1. And for 2 raised to n, that is always non-zero. So we are safe to use ratio test. Now let us solve for the limit of the absolute value of a sub n plus 1 all over a sub n. To get a sub n plus 1, just replace all the n's in a sub n by n plus 1. So we have -1 raised to n plus 1, 2 raised to n plus 1, all over the factorial of n plus 1. So this is a sub n plus 1, then divide this by a sub n. This will give us a complex fraction, so let us just multiply it by the reciprocal of a sub n. So times n factorial all over -1 raised to n times 2 raised to n. Here we have 2 raised to n plus 1 all over 2 raised to n. If we simplify this, we have 2 in our numerator. And for the factorial of n over n plus 1 factorial, recall that n factorial is equal to 1 times 2 times 3 up to n. And similarly, n plus 1 factorial is the product of the integers 1, 2, until n plus 1. And in this rational expression, we can cancel out the first n factors. And we are left with 1 over n plus 1. So we have n plus 1 here in our denominator. Now how about -1 raised to n plus 1 divided by -1 raised to n? That is equal to -1, but at the same time, we have absolute values. So, -1 under the absolute value will just be equal to +1. So, we only have the limit of 2 over n plus 1. And if we get that limit, as n goes to positive infinity, we have 2 over infinity, and that is 0. 0 is less than 1, and by ratio test, the series of a sub n is convergent. For our last example, let us consider this series, the series product of positive odd integers up to 2n minus 1 all over n factorial. So let's write that as a sub n. And again, before using ratio test, check first if this is indeed not equal to 0. A sub n is equal to 0 only if the numerator is 0. That is, if 2n minus 1 will ever be 0. But there is no integer that makes 2n minus 1 equal to 0, so we are safe to use the ratio test. Let us compute the limit of the absolute value of a sub n plus 1 over a sub n. For the a sub n plus 1, replace n by n plus 1. So in our denominator, n factorial will just be n plus 1 factorial. And for our numerator, 2n minus 1 will be 2 times n will now be n plus 1. So we have 2 times n plus 1, then minus 1. And if we simplify this, we have 2n plus 2 minus 1, or simply 2n plus 1. So our whole numerator is 1 times 3 times 5. So their differences is 2. So the term before 2n plus 1, that is 2n minus 1. So 1 times 3 times 5 up to 2n minus 1 times 2n plus 1. That is a sub n plus 1. Then let us divide it by a sub n. Equivalently, let us multiply it by the reciprocal of a sub n. So times n factorial over 1 times 3 times 5 up to 2n minus 1. There is no need to write the absolute value anymore since factorials are always positive. Similarly, our numerator in a sub n is always positive. So now let us simplify. We can cancel out the factors from 1 up to 2n minus 1. So let's write here 2n plus 1. And for n factorial over n plus 1 factorial, this is the same as our previous example. we can cancel out the first n factors and we are left with 1 over n plus 1. If we get the limit of 2n plus 1 over n plus 1, as n goes to positive infinity, we have infinity over infinity. So we are yet to multiply this by 1 over n all over 1 over n. We have 2 plus 1 over n all over 1 plus 1 over n. And the limit of that is now equal to 2. 2 is greater than 1, and so by the ratio test, our given series is divergent.